Hello, my name is Keshwani. That's Keshwani, Keshwani. We are here because we want to prepare for SAT. We have been solving SAT math problems out of this book here, the official SAT study guide. If you do not own this book already, purchase one immediately. You're going to need it. The problem that we are about to solve is the one that you will find on page number 468. Please turn to it. Today is our lesson number 24. 428. There are 4 questions there, gradient questions. These are all difficult questions. Let's take a look at them. Number 15. It says, again, you have to have the book in front of you so that you can read the problem with me. Page number 468. 468. It says, from a jar containing 50 pieces of candies. Alright, so we have 50 candies. Of which 25 are red and 25 are green. 25 are red, 25 are green. He takes 3 red ones and 4 green ones. He takes 3 red ones and 4 green. He takes an additional 30 pieces from the jar. Takes additional 13 pieces from the jar. What is the least number? Here's the tricky part. What is the least number of these additional pieces must be red in order for Ari to have more red than green? We want more red. The least. What is the least number of this addition? Least number, so that R is greater than G. Well, there is a straightforward and simple way to do this problem, which is to simply start out with what we have to begin with. So we're going to take 13 candies, and we want to draw least number of candies is what we are told. We have 3 to start out with. We have 3 of these. We have 3 of these, and 4 of these to start out with. Let's take a and we want to draw on the 13. The simplest and straightforward way is to split the 13 into half. Well, obviously we can't have 6.5 candies, so let's start with 6 and 7. Let's pretend that we took 6 of these and 7 of these. If we did that, we'll have 9 altogether. We'll have 9 of these and 11 of these. Here's the total. Total red and total green. We'll have 9 of the red one, as you can see, and 11 of the green one. And we are told that red has to be greater than green. We are told that red has to be greater than 3. That is not the case here. Red, we have only 9 of them, and we have 11 greens. So that doesn't work. Let's do the other way around. Let's have 7 of these and 6 of these. Let's see what happens. 7 plus 3 is 10, and 4 plus 6 would be 10 also. So here they are equal. We want red to be more than green. Let's try one more time. It can't be that bad. So let's have 8 and 5. 8 plus 5 is 13. That's what we are doing. We're drawing 13. Draw 13. That's what we're doing. 8 plus 5. Let's see what happens now. So we have 3 to start out with. We started out with 3, and now we have 8 more of red one, giving us a total of 11. We started out with 4 green one, and now we have 5 more, giving us a total of 9. And now we have achieved our goal. That's it. So the question was, what's the least number of red candies that we need to draw in order to fulfill the task? The answer is very simple. 8 of them. That's all. Only tries 3 tries. That's it. 3 tries and we got it. So we start out with 13. When you have a situation like this with 13, don't start out with the extreme scenario of 1 and 12 and then 2 and 11. Don't start out like that. Start somewhere in the middle, happy medium. So we have 13. If we had 14, I would have assumed 7 and 7. We have 13, so start out with 6 and 7, see what happens. If it doesn't work, change the scenario. Six red candies were not enough. If we had, out of the 13 candies that we're drawing, if we had drawn only six red candies, that would not have been enough. That's only 9. And that would have been 11. That doesn't do the job, so let's have one more red one. If we're going to have 7, this has to be 6 because they have to add up to 13. That doesn't do the job, that gives us 10 and 10. So let's do one more. If we draw 8 red candies, 3 to start out with, 8 more, that gives us 11. And that is more than 9 because we started out with 4 green. There is 5 more we are drawing here, so that's 9. There you go. That's it, we're done. The answer is 8. The answer is 8. The answer is we need to draw the least number of red candies that we can draw is 8, so that we have more red than the green. If we're going to withdraw 13 candies. Not withdraw, I meant to say draw. Do you understand? As in take out. Number 16. Number 16. It says a trifactorable positive integer is the product of 3 consecutive integer. A trifactorable positive integer is said to be trifactorable. For example, 6 is said to be trifactorable because 6 can be written as 1 times 2 times 3. 6 is a trifactorable. So is 990. 9 times 10. 9 times 10 is 90, or better yet, 9 times 11 is 99, and 99 times 10 would be 990. 990 is trifactorable. The question here is, 999 is said to be a trifactorable integer. Question simply is, how many integers less than 1000 are trifactorable? How many integers less than 1000 are trifactorable? Now that sounds like a pretty daunting task. There are 1000 integers. How the hell are we going to figure out how many are there? In reality, if you give it some thought, you will realize that this is actually a pretty straightforward task. Why? Because they have to be 3 consecutive integers. They couldn't possibly be, for example, they couldn't possibly be 11 times 12 times 13. That would not be the case. Why? Because we know that 10 times 10 times 10 is 1000. If 10 times 10 times 10 is 1000, then if this is more than 10 and this is more than 10 and this is more than 10, their product is going to be more than 1000. Their product is going to be more than 1000. Which means they cannot be more than 10. They cannot all be more than 10. That's what we have to understand here. They cannot be all more than 10. That limits our choices to very few. All we have to do is figure out how many there are. Do you understand? Let's do it. For example, again, the logical thing would be to start out with 1, 2 and 3. 1 times 2 times 3. Of course that will be less than 1000. Because as long as, if I have 3 numbers, for example, if I have 3 numbers, and if I tell you that this one is less than 5, or let's say if I tell you that this one is less than 3, and if this one is less than 3, and the third one is less than 3, and if we were to multiply them, I do not know what their product is, but whatever their product is, it's got to be less than 27. Why? Because 3 times 3 times 3 is 27. So if they are all less than 3, their product has to be less than 27. Here, this guy is less than 10. That guy is less than 10. 2 is less than 10. Say 3 is less than 10. Therefore, their product is going to be less than 1000. Of course, it's so simple that we know that it is 6. Let's do one more. 2 times 3 times 4 would do the job. Again, why? Because they're all less than 10. As long as they're all less than 10, first number less than 10, a second number less than 10, a third number less than 10, their product would have to be less than 1,000. That's all it is. That's all it is. And of course we know here that this one works out to be 24. 24. I need to move this 6 to the unit digit. Similarly, 3 times 4 times 5 again would be less than 1,000. It would be less than 1,000. If you insist, I'll write it down what actually it is. But we don't actually have to write down the exact product. All we have to realize that it is going to be less than 1,000. Similarly, 4 times 5 times 6, 5 times 6 times 7, 7 times 8 times 9. They are all less than 1,000. This quantity is less than 1,000. Why? For one very simple fact, because the first number is less than 10, second number is less than 10, third number is less than 10. So therefore, if you have 3 numbers, all 3 of them are less than 10, the product is going to be less than 1,000. Again, if you're curious, I'll tell you what it is. But you don't actually have to, in the exam, we don't actually have to waste our time to actually figure out what it is. It doesn't matter to us. 4 times 5 times 6 is 120. 120. This guy is going to be 6 times 5 is 30, 30 times 7. 30 times 7 is same as 3 times 7, which is 21, and a 0 at the end. And this one is going to be 7. Did I miss something? I missed 6, didn't I? 6, 7, and 8 is going to be 336. Again, we don't have to actually, I keep reminding you, we don't actually have to figure out any of these things. We just have to realize that they are all less than 1,000. So far there are 6. 7 times 8 times 9 is going to be less than 1,000. 9 times 10 times 11, as you can see right here. Oh, I missed the 8 again, didn't I? 8 times 9 times 10. Again, 8 times 8 nines is 72. If you multiply it by 10, you just have to stick a 0 at the end. 720. And finally, you can see there, 9 times 10 times 11 would be 990. And we don't need to go any more than that, because if we were to go more than that, 10 times 11 times 12, because they are all more than 10, their product is going to be more than 1,000. Their product is going to be more than 1,000. That's all. That's it. We're done. There are 9 of them. There are 9 of them. Oh, I didn't mean to circle this part. Sorry. I meant to say there are 9 of them right here. These are the 9 trifactorable integers. But as I said before, in the real exam, we don't actually have to waste our time to figure these out rather. We don't have to actually figure them out exactly what they are, because nobody is asking us what these integers are. They just want to know how many there are. There are 9 of them. All of these right here. There are 9 products. You start from 1 and end at 9. 9, 10, 9 times 10 times 11 is the last one you're going to get. It's already approaching 990. Obviously the other one is going to be more than 1,000. That's it, we're done. I will see you tomorrow, okay? Bye now.